Hello everyone, welcome to Professor 3Mac. Today we are going to learn about rotary forging and its simulation in ABAQUS CAE, and I will give you a step-by-step tutorial on that. As you can see on the slide on the screen, it's a high strain rate problem. We will be focusing on cold rotary forging. The dies will be rotating and impacting at a very high velocity, and also, as you can imagine, it's a complex contact interaction which we have to define and solve. This is a link from YouTube where they have shown how the whole process really works. As you can see, you have a workpiece. The dies are rotating, and at a high speed, it basically forges the component. In this case, we are working with cold forming. We are working with cold forging, but the process can be hot forging as well. And you can see you can make many different types of shapes as shown in this animation. I have a top die, as you saw just now in the video. We will have a bottom die, a workpiece. Both will be rotating, and then this die will be at a certain angle with some conical shape thing. You can have any shape as you like for the part to be manufactured. Then we will use ABAQUS CAE to cold forge using rotary forging process and form it into this kind of shape as you see on the screen. So at the end of the video, you will be able to learn this process as you see on the screen. This is the animation of the process where we are performing cold rotary forging using ABAQUS CAE. So let's jump into it. And see how we can make in ABAQUS CAE. I will first start with modeling the parts, upper die, bottom die, and the workpiece. So I will go with the create part option. Then I will select 3D deformable solid extrusion option. And I will create the component. All the geometry, material parameters, and loading conditions are taken from a research paper. I will post the link for that paper in the description below. So I will first create a circle, then give a depth of around, let's say 15 millimeters in this case. And then I will create the second part. Now I will work on the dies. So for the dies, I'm going to use analytical rigid surface, and I will use the revolved shell option. Again, the dimensions are taken from the paper, so have a look at that. You can also download the model from my website, www.professor3mac.com. So I'm just going with a certain angle to have that kind of shape, conical shape as we need. Again, this is just approximate geometry I'm making. So I will just press done, and then it will revolve when I have the shape of the die. A small conical shape. I don't know if this is enough or not. Let's see how it looks like. And since it's a rigid body, so we need to create a reference point because all the loading and boundary conditions will be applied on that. Now the bottom die, I will use the same option, analytical rigid, 3D, and revolved, and I will create a bottom die which is a cylindrical shape at the bottom. So again, the similar dimensions as the top die, and then I will press that's done. And again, I have to create a reference point for this because it's a rigid body, so we need to have a reference point where we can apply all the deformation, boundary condition, etc. Okay. Now we need to define the properties. Both the dies are rigid in this case. The only thing we have to define is the material properties for the workpiece. So I will go with the create material. I call it workpiece in this case. Again, the properties are assumed and taken from one of the research papers. So density, since if everything is in millimeters, then the density should be in tons. If everything is in meters, then it should be kilograms per meter cube. So that's what I have done here. Then elastic part of the simulation, elastic part of the material properties. So Young's modulus is 210 megapascals, gigapascals, so it's 210 megapascals, and 0.3 is the Poisson's ratio. Next is the plastic part of the properties. If we are doing a hot forging process, and we have to define thermomechanical properties, so everything should be dependent on the temperatures. In this case, we are working on cold forming, so we will be working everything at room temperature, ignoring any temperature effects. So again, I'm using a bilinear curve in this case for plastic part. In the actual research paper, they had a non-linear. Okay, now for the part one, we need to create a solid section before we assign the properties to the part, solid homogeneous, and then select the workpiece material properties, which is the only one we have defined, and then we select assign section, select the part, select the section one, which is the only section we have created, and press OK. It's done. Now we have assigned the material properties. We will instance the parts here, and assemble the whole process setup. They are all over the place, so we're gonna auto offset, in my opinion, so that we can then translate them and adjust as we want for the process. So we need to rotate some of the components. As you can see, the workpiece is in a different plane, and also we need to translate the object. So let me do that now, and in the most convenient way possible. Again, you can have your own ways of doing it, but these are just simple operations you can do. So everything should be aligned at the center of this tip here, and this is the top die, as you know. So let's start doing that. I'll first start with the rotate option. I will rotate this thing around about x-axis, because it has to be, the flat surface should be aligned with the top and bottom die surfaces. So I need to define the vector about the orientation, so it will be the 0, 0, 0 region and 1, 0, 0 or whatever, and then I will rotate it by 90 degrees, and that's it. So now it's the flat surfaces are aligned with the dies. Next is we need to translate all these objects together and bring them in the same setup as we need for the adjusting. So I will bring this at the center here, the translate option, then I will do the same for the bottom die. I can check if there is a small difference or not. Small distance between the top and bottom die and work pieces as well, so that they don't really penetrate into each other before the simulation starts. And now I will translate this as well and align it with the bottom part surface of the workpiece. So here I will translate it like this, and it looks good, I think. Then, and if you see now, everything is aligned as we want in that. Now in the real time, we have the top die at a certain angles, because we don't want to apply the pressure on the center, which is the maximum if it's a flat die, and this is the one of the advantage you use. So you have an inclined die, and that rotates. So that's what I'm going to do now later. So we'll rotate it around axis in this, that axis in this case, and I need to define the vector, which will be 0, 0, 0 and 0, 1, 0, or you can select the Z axis. And again, I need a small angle, which is again I'm taking from the paper. They had many different ranges of angles, and I'm selecting one of the angles just to show the ways you can do that. So the distance is a bit large, so I will try to bring it closer so that we don't need to spend too much time solving this. When you bring it, the points together, you can see some of the surfaces are intersecting on the left hand side. So need to bring the eye slightly up in y direction, so that we don't have initial contact already established, or they are already going through the one another. So I'm going to translate the top die again in y direction. Yep, and then I will give a very small distance in y direction. Let's give something like 0.0. That might be too much. Go back, change this value to a smaller value now. So let's make it 0.25, and this looks decent. Yeah, and there is a gap, so let's go with that. Hopefully this should be fine. Okay, now step definition. For this analysis, it's a very fast process with a lot of inertia involved, so we're going to use dynamic explicit step. If you're doing hot forging, then you need to have a temperature displacement based explicit analysis. So everything is default for the time being. The total time of simulation in this case is 3.5 seconds for the forging process. Direction, we have to define the context between all the surfaces. So you can go with the general contact, or you can use surface contact as well. Let's see what happens. Because you have analytical rigid surfaces, so we need to define the surfaces so that ABAQUS knows which surface it has to look for. So I'm going to go with the surface to surface contact now. I will create surface, round surface, and then I will select the top surface of the workpiece. Okay. But you can go with general, but you need to define the surfaces for each component, because for rigid components, ABAQUS struggles to find. ABAQUS needs us to define the surfaces separately. Now we define the interaction properties, contact, tangential behavior. I'm assuming it to be penalty with the friction coefficient is taken to be 0.15 again from the article. For normal contact, we will be using hard contact formulation, and they will allow separation as well if you retract your dies, etc. So this is done. Now we will do the same for the bottom surfaces. Surface to surface contact, die surface, again brown is the outer surface, so we select that, and now we have to select the bottom surface of the workpiece. So I will just remove everything and just keep the workpiece so that I can easily select the internal surface of the work itself. Oops, I removed the long one, so I already selected that. Let me bring back and I will remove the bottom die, and now I can rotate and easily select the bottom surface. That's pretty much it. And I will use the same interaction properties as for the top interaction for time being. In my opinion, bottom should be tied with the workpiece, but let's go with this for time being. Now I go to the loads and I will start applying the loading and boundary condition as per the process parameters which were provided by the article. For displacements, in this case, we're gonna fix the upper die in X, Y, and Z direction, and we will restrict all the loads, all the rotations as well, except for the rotation about Y axis, which is UR2. So we need to rotate the die in UR2 direction. Similarly, we will provide now the angular velocity, which is given to us, which is the rotational speed of this die, and that will be VR2. And that will be around since they gave us the RPMs, I'm just converting those into the radians per second because ABAQUS applies rotational speed as radians per second. So I'm converting those revolutions per minute into RPM multiplied by pi, and that gives me radians per second, and that is around 31.416 radians per second. So I'm going to copy this value and apply as the rotational speed about y-axis. It's shown here now. So this one is good. Now we need to do the same for the bottom die. Okay, displacement, select the bottom die, and I'll fix everything for the time being. Allow the rotation. Again, the boundary conditions are not clearly defined in the paper, so I am just going with my own assumption. Let's see, and we'll get back to that again because we still have to work on defining the local boundary conditions, local coordinate system to define the rotation of the top die, because it is now aligned at a certain angle, and if we rotate it now, it will be rotating at that or about that. So again, as per the paper, the die from the bottom side moves upwards with a speed of 3 millimeters per second. So that's what I'm applying here. And all the other dimensions or all the other degrees of freedom are fixed for the time being. I will get back to, we will refine these boundary conditions as we move on depending on the process requirements, since the paper doesn't clearly explains all the boundary conditions. So let's move on. Let me double check everything. So I think for the time being, I'm fixing the rotation of the bottom die, because then otherwise everything will be rotating and there will be no the contact area might not change for the workpiece on the top die. The the actual case, we need to constrain they have constrained the surface of the workpiece with the bottom die. So the workpiece rotates with the bottom die. And that's what I'm trying to do here, but I think this might not be appropriate for this kind of simulation, because but let's go with that now. So now I'm just using an approximate mesh. Again, you can do your own mesh sensitivity analysis, get the more accurate results. So this is the mesh I'm using. Again, everything is default. Element type, I can just show you now. So this is 3D stress and reduce integration into elements for explicit case. If you don't select explicit or standard at the top, it automatically converts for whatever it is. You can also use ALE, adaptive meshing, if you have a huge amount of deformation to get better convergence, but we will look at that later. So now I go to the job and I submit. Call it Rotary Forge 1. And I will always go with the double precision and full precision forever. And now I will submit to see if everything is working fine. It's aborted, so let's look at the error, what is happening there. If I go back, I need to define, I think, so kinematic contact is not allowed for rigid body with multi-body constraints. They were mentioning something like this, which they have used. When I try to use it, I think ABAQUS doesn't allow this, so they might have used something else, and they try to explain in a different way. So what I'm going to do now, I'm going to go back and try to see how I can remove this error. And this is what happens. You build your model, even though you are an expert, you find some issues, you go back, make some assumptions, find some compromise, and make your model work. So I think this might be the thing which is causing problems. So I will delete this for the time being. I think for me, the best would be if I can use a tie constraint and tie the bottom surface of the workpiece with the bottom die, because it has to rotate rather than constraining that. So maybe they were trying to explain that here as well. But again, there are other options as well, so you can explore those. Let me do that now. So for that, I will have to remove the contact surface interactions with each other, or I can just deactivate that as well, which is the easiest thing. So, and then I will create a tie constraint between the two. Again, depending on your own problem, rotary forging has many variants, so you can select your own boundary conditional loading. So I don't need this surface, I need the bottom surface of the workpiece, and then the top surface of the bottom die, which is this one. Then this will tie the surfaces, which may not be exactly true, but depending on your whole rotary forging variant, you can use this. Now let's submit this and see if we are able to eliminate the error. Fingers crossed. Monitor. It went through to the solution step. This means now that error has been resolved. It's going to take some time because explicit is generally CPU intensive, so it requires CPU power. As you can see, it is running now. So I will get back once it is done, or at least it's at a stage where we can see some of the outputs. So as you can see, the analysis is running now, and results are there. I will show you the results at the end, but the first thing we have to do is we need to rotate the top die about its axis rather than the y-axis, because right now our boundary condition says that rotate about y-axis, so it is not rotating at that axis, at the actual axis of the thing. So as you can see, the analysis is working. So what I'm going to do meanwhile, I will modify the boundary condition. You can see the rotation is not about its axis, but rather on y-axis. So I'm going to create a datum plane which will be aligned with the actual axis of the component. And you can see this is this has to be on the datum coordinate system. So I created the datum coordinate system, and now I have applied it to the datum coordinate system too. And since everything is fine now, so I already terminated the analysis, and I will rerun it again because now the boundary condition is okay. Yeah, so the problem is we have defined the rotation around the local coordinate system while the rest of the boundary conditions are around the global coordinate system. So we need to change that. So we need to go back to the loading step, change that as well. That's what I'm going to do. So again, you see the problems always come in and you need to read carefully the error message and then go back and sort it out. So I'll go to the load module. I will change the datum plane for the other boundary conditions in the same reference point as the datum plane for datum coordinate system, which we have defined. If anything is not clear, you can always ask me and I will try my best to reply to you as soon as possible. Sometimes I'm busy, I can't reply, but I will definitely get back as soon as I get time. So that's what I'm doing now. Everything is now set up. If I go back, go back to job and then submit again, and hopefully it should move on. So we don't have that error anymore because now all the boundary conditions for that reference point are in the local coordinate system. So it goes well, started running. So now I will get back to you once I have some results ready for us. So as you can see, it has gone through a lot of increments and we have a lot of steps out as an output. So let's have a look at the results rather than running it for you. So as you can see, this is the initial stage. And if I play the video, then you can see the rotary forging is working. Everything is simulating very well. As you remember, the bottom die is tied with the bottom surface of the workpiece. In reality, it should be constrained or coupled depending on if there is any stick slip condition between the two of the dies. Again, depending on the process variance. Again, if I remove the top die, then you can see how the rotary forging really deforms our workpiece in different views. In this case, we are not using any adaptive ALE type adaptive meshing, but if you have a severe deformation, then it might be worth having that to get more accurate results. And again, you can see everything is looking great. To do the use of ALE, you go to the step module, select manager, and then in this case there is no ALE meshing, so you press edit, and then you select use ALE meshing, and you can change the frequency, etc., and press. You have to select the region first because we have the workpiece, so we will select that. From viewport, select the view test, and now if you press OK, then you have the default ALE adaptive meshing. Now you can go back, rerun it, and see if there's any difference or there's any advantage if you have, especially if you have severe plastic deformation and very intricate shape produced through rotary forging. So again, I am running it, but I'm not going to go through the results now. So the short of time, you might have been already bored by now as well. So I hope this made sense, and now you are able to do such kind of cold rotary forging simulation in ABAQUS. Anything which is not clear, please get back to me. Every problem is different. Every rotary forging can have a different loading and boundary condition depending on the process variance. So again, it depends on you how much approximations and how much accuracy you want to really predict. So good luck with all this, and any questions, then please get back to me. You can always download the model from my website, and please don't forget to like, subscribe, and share. Thank you.